Hi, my name is Ryan Rogers, and today I'm going to talk to you about my undergraduate capstone project in mathematics from Euclidean spaces to metric spaces, supervised by Dr. Ning Zhang in the Department of Mathematical Sciences at the University of Cincinnati. We'll begin by defining a metric space. Let X be a set and D a function, which we call a distance function, mapping the cross product of X and itself onto the real numbers and satisfying the following properties for all P, Q, and R in the set X. First, the distance between P and Q is greater than or equal to 0, and the distance between P and Q equals 0 if and only if P equals Q. Secondly, the distance between P and Q equals the distance between Q and P. Lastly, the distance between P and Q is less than or equal to the distance between P and R plus the distance between R and Q. The pair XD is called a metric space, and D is called the metric. We call D a distance function because the aforementioned properties are analogous to the intuitive properties of distance. Distance is non-negative, the distance between 2 points is 0 if and only if the 2 points are the same, distance is symmetric, and the triangle inequality holds. Now referring to the set of real numbers as R, a Euclidean space is a set Rn where n is a positive integer denoting the dimension paired with the standard Euclidean distance function which serves as the metric. It is immediate from the definitions that every Euclidean space is a metric space. However, not every metric space is Euclidean. To see this, consider the set of real numbers paired with the distance function d so that for all real numbers x and y, the distance between x and y equals 0 if x equals y, and the distance between x and y equals 1 if x does not equal y. One can check that d is indeed a metric, and it is called the discrete metric. On the real line, using the Euclidean metric, the distance between 2 and 4 is, of course, 2. However, using the discrete metric, the distance between 2 and 4 is 1 since 2 does not equal 4, and it follows that the metric space we are considering is not Euclidean. Thus, every Euclidean space is a metric space, but not every metric space is Euclidean. In the paper From Euclidean Spaces to Metric Spaces, we consider and prove 6 theorems which hold in Euclidean spaces and determine whether they hold in general metric spaces. If so, we provide a proof. If not, we provide a counterexample. Thank you very much for listening.